Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel where I talk about everything I want to, science and math related. And this is chemistry class, unit 4, where we're talking about bonding and something called periodicity. Did I read this book to you yet? No. Okay, so we're going to start with this. I'm going to read to you this very important scientific book. Okay, it's called People in My Family. Okay, it's old. It might be out of print. Okay, it says, it's from Sesame Street. You know, they're all about education. Oh, I've got 5 people in my family, and there's not a one of them I'd swap. There's a sister and 2 brothers, a mother and a pop. That's me. 5 is such a lovely number. I'm awfully glad I've got 5 people in my family. 1, 2, 3, 4, 5. There's a little foreshadowing right here of the coming conflict. Well, I've got 5 monsters in my family, and we have lots of fun. Furry wife and scary husband. Fuzzy daughters, hairy son. 5 is such a scary number. Oh, I'm so glad that I've got 5 monsters in my family. 1, 2, 3, 4, 5. Now here's the climax. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They're scared of each other. But here's the denouement. Remember that term from literature? 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. Very good. And then here's the little questions if you're learning to count.
They should have ate the other people.
They didn't. They all got along and had a picnic. All right, now what in the world does this have to do with chemistry? Okay, no, actually it does. Okay, so here we've got the periodic table. Okay, and so the columns going up and down are also called families. Okay, so everybody think about that. The columns going up and down are also called families. The rows going across are called periods. So you can remember the difference that if this was a calendar, a period of time would be like a week, a consecutive period of time. You wouldn't call every Monday a period. A period of time would be like a week or 2 weeks or a fortnight, okay? But the families are the columns that go up and down. Now, this is a chemistry concept called periodicity, okay? And this is what it is. Look back at the book. Here are 2 families. The families have characteristics that are similar. The monsters look like monsters. The Muppets look like Muppets. Do you agree to that? Yes? Everybody sees that? Okay. Also, the families have members that are similar. They both have a father. How can I tell that these are the fathers? What do they have in common?
A mustache.
They're kind of, he's got a mustache and maybe he's got a little more hair right there, but look at what do they have in common? What are the same about them?
They're both in the corner. They're big.
They're both the biggest. They're the biggest ones. Maybe where they're placed. Maybe they're both in the corner. How else can we tell that maybe that they're the fathers? What do they have in common on their face? Not so much a mustache, something else. It's their eyebrows. Look how they've got the heaviest eyebrows in the family. Do you see that? So they have something in common. Also notice the smallest child. The smallest child in both families is pink. They're the smallest one. But now look at just the monsters. What do the monsters have in common? Their hair. They're all fuzzy. What else is in common with them?
They're ugly.
Why? Tell me more specifically. What do they have the same? What? They're monsters. But what is it? Look at their mouths. Are their mouths shaped the same?
Yeah.
Yes, they have common mouths. Look at their eyes. Their eyes are more googly-eyed. Do you see that? So they have more comic things in common. The Muppets, their mouths are similar. Their eyes are similar. Their skin texture is similar, where the monsters are fuzzy. So this is why it has to do with science. In the periodic table, the families, the columns going up and down, have more in common with themselves. The families are the same. The reason why goes back to 1s2 and 2s2 and then comes 2p6. Electron configurations, yes, they're really slick. It's the electrons have the same configuration of the valence electrons in each family. That causes the families on the periodic table to be the same. Now, just like these families on the periodic tables, there's the big elements and there's the little elements. And the representative elements on their period also have some things in common. But the commonness of the family is the big one. The period does have some representative members. Look at that periodic table over there. Notice that in family 1 and the helium's family and helium's family, that for both of those, the smallest ones are so small they're gases. Also, if you look at like nitrogen's family, oxygen's family, fluorine's family, all of them, the smallest one in that family is so small they're gases. Where if you go down in those families, the largest ones, if you look at bismuth, polonium, actinium, those are solids. They're so big, they're solids. So there are some things in common. Also, as you get bigger, they're more likely to be radioactive. So if you look at the first family, hydrogen's family, cesium is radioactive, francium is radioactive, and so is radon over there in the noble gases. So there's some things in common with the members, but cesium has more in common with hydrogen than it does with radon. Can you follow the point there? That even though the elements that are in the same period have some things in common, the families have more in common with each other. So the element, say fluorine. Fluorine has more in common with chlorine, bromine, iodine, and its family of halogens than it has in common with oxygen and neon and nitrogen and carbon with its period. Families are stronger than periods. Good? Sophia, you okay today? You following along? Taking your notes? You don't have your notes in front of you. Do you need something to write with? Because I've got some extra pens and pencils over there if you need them. All right. If y'all ever need a pen or a pencil, that little pot over there, including that yellow notebook, are free for the taking. So if you ever need one, just go ahead and get that. All right. Okay, so let's bring it back down to our notes then. Does this concept seem pretty good? You got this concept? All right. See, you can tell the moms are the same too. They both have orange curly hair. So they have a little something in common too. All right, so people in my family. Okay, so that is the name of our book here. So this is the first thing we're going to talk about, people in my family. So the columns or families are more like each other than the periods row that do have similar members. Now, the next thing is, what do elements want? And I'm going to stand over here to teach y'all this, but I'll point to that over there just for the video people. I know everybody's here today, but they'll probably maybe out fourth period, and then they'll have to watch the video. And if I keep running out of the video, it's kind of bad. Okay, so here's a little periodic table here, and I'll point to that one off screen too. Okay, so if you know, this is also the concept called periodicity. If you know what all the elements want, then it's easier to know everything about chemistry, if you just know what they want, okay? So the very first thing is, they all want to feel like a noble gas. Remember the noble gases? They're this column all the way over here, and they are the ones that have full valence electrons. So they want to feel like a noble gas, They want to feel like a noble gas, and they want to have an octet, which is they want 8 electrons in their valence level. It's not really 8. They want full valence electrons. Because if you look here at helium, it does not have 8 electrons in its valence level because it only has 2 electrons. It can't have 8. Does that make sense to you? But all the rest want to have 8. So hydrogen and helium want to feel like they have 2. Everybody else wants 8. Now, this is called the octet rule. And the scientist who figured it out, he said there are patterns in nature. Remember, we've talked about that before. And so a lot of early scientists would look at patterns in nature to discover things. He said there's patterns in nature, and in music, the scale has 8 notes. And that music is natural, and the atom is natural. So he said, like music, the atoms all want to have 8 electrons in their outermost energy level. 8 valence electrons. Well, the other scientists said, that's stupid. You're completely wrong. There's no way that music and chemistry have anything in common. And he died. And then after he was dead, they went, oh, he was right. Sorry about that. So I really hope that in the afterlife, he found out that he was right. And that they were wrong for calling him stupid. So that kind of goes back to our STEM idea. Remember, one of our things on our rubric for teamwork is you don't call other people's ideas stupid, that you build off of them, that you, the part of scientific inquiry is sometimes it takes going through a lot of bad ideas and failing and stuff like that to get to the good idea. All right, so the octet rule, they all want 8. Now, the next thing is, if you think of it, so to get this feeling of an octet rule, they do things with their electrons. And if you think about these electrons as children, it's a little easier to remember what they want, okay? So we're going to think of our electrons like children. They're the little atom's children. So there's the kid, the children, okay? Now, on the periodic table, the alkali metals, right here in this first column, this first family, what they want to do is they want to lose an electron. If you think about their electron configuration, they all end in S1. Does that make sense to you? So therefore, if they could lose that electron, they would feel like the noble gas before them. And their valence electrons would have 8. Can you imagine that? So I say that these in this alkali metals, that these are the bad parents. These are the ones who leave their baby at Walmart. It used to happen all the time. People would be looking through the canned food and then boom, there's a newborn on the shelf, just right there next to the peas. And they would just decide they don't want their kid and they'd leave them at Walmart. And they would be this abandoned baby. They'd find them in a dumpster. They'd find them whatever. Now we have a law that if you don't want a baby, you can take it to the fire station and leave it, and they won't arrest you for being a bad parent. You can just, because it's safer than leaving a baby in a dumpster or leaving them on the shelf at Walmart. So those are our bad parents who want to get rid of 1 electron. They have 1 extra child, they want to get rid of it. What about the next ones, the alkali earth metals? How many do they want to get rid of? 2, because if they could get rid of 2 electrons, they would feel like the noble gas before it. And so alkali metals and alkali earth metals want to lose electrons. Now, over here, the noble gases, they're perfect. They're William and Kate. They're happy with all of their children. You know, the prince and princess in England, Meghan and Harry. I don't know if they're princes and princesses anymore. I think they gave it up. But anyway, the next family next to them are the halogens. Halogens are the salt formers. If they could just get 1 more electron, then they would feel like a noble gas. Does that make sense to you? If all of them could just get 1 more, then they would have an octet. So they want to gain electrons. Now, I say these are the crazy parents. It used to happen a lot, but there would be people, especially women, who would be crazy wanting a baby. And they would dress up like a nurse. You see the little nurse drawing there? And they would go to the hospital and steal a baby. and they would steal this baby because they wanted to have one so bad and couldn't for some reason. So when you have a baby now, though, what's cut down on is they put this little metal thing on them that if the baby is taken beyond the doors, the hospital goes into lockdown. The door slams shut, the hospital locks down if a baby is removed from where it's supposed to be. So, you know, that made me feel good when I had my babies and that nobody was going to steal them. But then my youngest son, Joshua, when he was 10 days old, he got RSV. It's kind of like COVID. It's a respiratory virus. And he only had a 50-50 chance of living. So he was at Scottish Rite, and I wanted to know what their baby security was. You know, so I asked the nurse, I said, you know, why doesn't he have that bracelet on that keeps someone from stealing him? And she looked at me. It was this kind of large nurse, and I'll never forget it. She just laughed and said, honey, nobody wants your baby. He's sick. They don't want him. And I was like, oh, I want him. So they don't have any baby security at Scottish Rite because nobody wants those babies. They're sick. They wouldn't be any good. Like, you know, if he had gotten taken out of the hospital, he would have just died. He only had a 50-50 chance in the hospital. So anyway, some people want to steal babies, but not from Scottish Rite. Okay, so the other one is, so the ones near the noble gases want to gain electrons. So the halogens want to gain 1 electron. How about oxygen's family? How many do they want to gain? 2. And nitrogen's family? 3. Okay, so those are the ones that want to gain. Now, what about these here in the middle? Wait a minute, did I get... Oh, we got to do this one first. Okay, now carbon. Carbon is not 4. Carbon is too far away. You might can steal 1 kid, you might can steal 2, you might can even steal 3. But stealing 4 kids is going to be a challenge, isn't it? So carbon is not with the stealing idea. Instead, all of these nonmetals, and especially carbon and silicon, they will work out sharing arrangements. So these are the parents that some of y'all have in this room. What kind of parents share their kids? Work out sharing equipment. You go to court and the judge tells you the sharing arrangement. The family court. What kind of parents are those? Divorced parents. I bet some of y'all have divorced parents in here. Statistics would say that some of your parents are divorced and y'all have sharing arrangements. So the divorced parents, they are non-metals. Non-metals work this out between them. There are divorced parents and they have sharing agreements. So there's our little divorce decree down there. All right, so, and just like real divorced parents, most divorced parents do not equally share their children, do they? Usually the mom gets the kid more, sometimes it's the dad, but very rarely is it equally, where you go to mom's on Monday, dad's on Tuesday, mom's on Wednesday, dad's on Thursdays, right? No, you're usually with mom through the week, dad every other weekend, and in the summer is how the normal arrangement is. So mom usually gets the kid more. Not always, but usually. I did know one family that they bought houses next to each other, the mom and the dad, and the kid did do Monday mom, Tuesday dad, Wednesday mom, Thursday dad, because they were next door neighbors. And one of my kids in my other classes said, they must really have still got along pretty good, because they said, my parents the kid was saying that their parents were divorced, and that would never work out for them to be next door to each other. So, anyway, so our elements, some of them do share the electron exactly equally, and that's when they're the same element. So like oxygen will share electrons with another oxygen exactly equally. They're called diatomic, di meaning 2, and it's usually when something is bound to itself, and the diatomic elements actually kind of make a 7. It's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine. See how it makes like a 7 plus hydrogen over there? You'll have to memorize those. I don't know if it's for this test. I'll look and see. But you have to know the ones who share. Those are our crazy divorced parents who exactly share their kid. All right, now the ones in the middle here. The ones here we have not talked about, the transition metals, copper, gold, silver, nickel, these famous metals right here. These are hippie parents. They're hippies. Let me tell you about the hippies. These are our hippies. Okay, so in the 70s, there was this ideal about raising children, that the best way to raise children is with no rules. Okay, so there were these hippies, you know, peace and love, long hair, not many baths, that would live in communes. So they would all live together. A lot of them were out west in California where the weather was good and stuff. They would all live together, and they didn't believe in rules. So they didn't believe in sexual rules. There were no marriages. People could just be with whoever they wanted, have babies with whoever they wanted. And so the babies, the kids, would run around these hippie communes, and often they would call all the men of the commune dad, all the women of the commune mom. And because a lot of times they didn't even know who the dad was, you know, free love. This was what was going on in the hippies, okay? Drugs and love is what was going on. So this was a real ideal. And they believed this was they truly believed, you know, peace and love, no war, make love, not war. And they thought that these children, this was the ideal way to raise them. They were usually dirty with stringy hair, if you see pictures of them. And you heard this in songs. It was an idealized thing. There was a song from Bobby Sherman called Seattle, and it says, growing up like a child, beautiful, free, and wild. It was this idea that the best way for children to grow up was free and wild. There was another song that talked about it too. Oh, well, born free, free as the wind blows. That also has that ideal that the best way to raise children are with no rules, and they just go do whatever they want to do. So it was a real big deal, and they would let their children run like this. Now, something killed it. Anybody know what killed this hippie commune movement? Anybody know what killed it?
The viruses.
Wait, say one at a time, what? The 90s. It died before that. What else did you say?
Sickness.
No? Someone knew in one of my other classes last semester. It was Charlie Manson. Anybody heard of the Manson Murders? He was in charge of one of those hippie communes like that. And people, you know, the society in general thought the hippies were great, they were peaceful and all that, until Charlie Manson, and they killed all these people. Sharon Tate, it was the Manson family murders. Once they became, and they were crazy, carved swastikas in their head, girls shaved their heads. He didn't do the murders, his disciples did. Well, that was the end of that. People started saying that maybe this wasn't such a good idea after all, and you know, those kids probably all went to defects by then. So that was sort of the end of that. Okay, so now what does that have to do with chemistry? That's what these metals do. What the metals do is exactly what I told you. Remember how the children called everybody mom and dad? The children, the electrons with the metal, are not assigned to a nucleus. The electrons can just go wherever they want from one atom to another. That free flow of electrons is what gives metals their properties. It's why they're good conductors of heat, why they're good conductors of electricity, why they're shiny, why they're ductile and malleable. Every characteristic of metals comes from this idea that they don't hold their electrons to themselves. They let the electrons be little hippie children and run around wherever they want to. Okay, can you imagine that? So they let their electrons run wild and free. Wild and free electrons. Okay. Now, there are 4 things of saying the same thing, okay? And all of them have to do, I need to explain a little bit more about the children. Okay, so as you look at these families going down, they get more and more electrons, right? So like lithium has more electrons than hydrogen. Sodium would have more electrons than hydrogen. Do you see that? Everybody follow that idea? Okay. So once once you have these, as you go down with more and more electrons, there are a few things that come into play. One is that, and I always say this is like me and my sister. Okay, so my sister had 6 kids. and they were allowed more freedom than my 3 kids were. My 3 kids, I usually could keep up with them. You know, I knew what they were doing and stuff like that. Her 6, they were close together, and 6 of them, they had a lot more freedom. And I would be over at her house, and there'd be a kid doing something bad out on the edges. Usually it was David. Shh, don't tell him I said that. I love you, David, if you watch this. But he would be off doing something bad. But he was really smart. And he would make sure that there were at least 2 or 3 kids between him and mom whenever he did something bad. So, my sister would have to, wade through the children to get to David to punish him. So he just got away with it. He just got away with it. Now, if there was a kid right next to her who did something bad, they might get a spanking, they might get their toy taken away or whatever. But not David. He always made sure he was out of arm's reach, okay? How that works is with elements, it's called the shielding effect. Electrons that are close to the nucleus, they can feel the power of the nucleus, and they are held tight. Remember, the nucleus is positive and the electrons are negative, and opposites attract. But if there are enough electrons between the nucleus and an outlying electron, it'll be able to get further away. There's less power of that nucleus upon the electron. It's the shielding effect. Everybody understand that? Now, here's the next thing. I would go with Gail and her kids to Walmart, and they would scatter. 6 kids in 6 different directions. She might keep the baby close. Everybody else running, playing in the clothes, hiding in the middle of the, you have clothes hanging up in a circle. They would hide in the middle and then be popping out. Over in the toys, riding the bikes. They're everywhere. They're just gone, okay? But with me and my husband were infertile. It was very hard for us to get our kids. I really held them close and precious. I'd never let my kids just take off wherever they wanted to in Walmart. If there was a child thief, who would be easier to steal? My sister's kids or my kids? My sister's kids, right? They've spread on out. They've gone wherever. If you find them hiding in the middle of the clothes, then you might could get them. Mine, in fact, because stealing children had gone up by the time my kids were little, when I would go to the grocery store when my kids were babies and I turned to get something off the shelf, I would keep a hand on my kid as I turned to look at what was on the shelf. I would not turn my back on my kids without touching them. Nobody was grabbing them without me knowing it. My niece, my sister's older than me, so she's got grown kids who are married and have kids. Okay, so one of her children is married, and when her husband was a little boy, he was about 3, his dad was walking through a store with him, looking at stuff. A man came up on the other side and grabbed his hand and started pulling him away, trying to steal him. Just grabbing him and pulling him. I think it was in South Carolina, not here. But still, watch your kids, okay? So now what does that have to do with the atoms? It's this. The atoms try to take electrons from each other, right? So the energy it takes to take an electron is one of the things we look at. How closely atoms hold their electrons in is another thing we look at. Do you think a chlorine holds its electrons closer or a sodium? Who's going to hold their electrons closer, chlorine or sodium? Chlorine, because chlorine wants to keep all of theirs and steal someone else's. Sodium wants to get rid of theirs. They don't hold them close at all. So this is our 4 ways of saying those ideas, okay? The first one is called electronegativity. It's the ability to attract electrons to oneself. And I might start writing the abbreviation. Electrons is that. So this is the electronegativity is the fancy science way of saying how good are you at stealing electrons? So, and how close do you hold those electrons to yourself? The ability to attract electrons. So chlorine has a high electronegativity. Sodium has a low electronegativity. Does that make sense to you? Okay, here's another way to say it. Ionization energy. This is the energy it takes to remove an electron. How much energy does it take to remove one? Would it take more ionization energy to take one of chlorine's electrons or sodium's electrons? Chlorine's. Y'all are doing so good with this. This is good. The next one is called the shielding effect. And it's the power of the nucleus is blocked by electrons. So the more electrons you have, the more the outer ones are shielded and the further they spread out. The power of the nucleus is shielded, shielding effect. And then element size, and this is the weird one, okay? As you go down a column, the atoms get bigger in every single column. Does that make sense to you? But as you go across the rows, the atoms are getting more protons, more neutrons, more electrons, but they get smaller because the nucleus is holding those electrons in tighter and tighter. Can you imagine that? It's getting more protons and more neutrons, more electrons. It doesn't matter. They get smaller because the nucleus is holding its electrons tight, like how I held my 3 little kids tight. Where Gail, my sister, she was an alkaline earth metal. She was letting them spread out wherever they wanted to go. And you know, it all worked out. Her kids grew up, my kids are in college, so mine weren't too overprotected and hers were fine. But oh, they had some stories to tell. Okay, so as you go across the period, the size decreases. Surprisingly, the size decreases. All right, everybody good with that? That is called periodicity. That's the concept. It's considered one of the hardest concepts in chemistry. But if you think about children, it's not so bad. But you have to study, or else it's real easy to get these words mixed up. Now then, I want to show you, do y'all have a periodic table drawn in your paper there? No, you don't. Okay, draw a little periodic table like right here. Just draw a little square over to the side. This is your periodic table. It's drawn as a square, but imagine that's a periodic table. Okay. And we're going to look at 1, 2, 3, and 4, the trend. Okay. So as you go down a column, electronegativity, the ability to attract electrons to oneself, as you go down, I'm going to change the colors here. It'll be easier to see. I'll make it green. Okay, so number 1, we're going to make that green. And as you go down a column, it decreases. So the more electrons you have, the less you can attract them to yourself. Does that make sense to yourself? As you go across, it increases. Because what they want electrons. So electronegativity, the ability to attract electrons to oneself, as you go down a family, it decreases. As you go across a period, it increases. Do you understand? Okay, now I'm going to change the color. Now we'll go to blue. Okay. So for number 2, ionization energy, the energy it takes to remove an electron. As we go down a family, is that going to increase or decrease? As you go down, it is going to decrease. That energy takes less. Does that make sense to you? As you go across, what does it do? Does it take more or less energy to remove it? More, so this energy increases. These two are the same. It increases for number 2. Shielding effect, number 3. We'll make it orange. Well, orange is kind of close to that one. Yeah, we'll make it orange. Okay, number 3 will be orange. Shielding effect. As you go down, for number 3, What was shielding effect going to increase or decrease? It's going to increase. There's going to be more shielding effect. So shielding effect increases. You can do this all neat on yours. And as you go across for shielding effect, because they're getting smaller, but they're getting more electrons, there is no change. No change. You can put no triangle. Remember, we can do triangles for change. Does that make sense to you why there's no change? The two things counterbalance each other. Yes, there's getting to be more electrons as you go across, which would make it seem like it would increase, but the atom is holding them closer, and it takes that away. Can you imagine that one? Okay, so the fourth one is the element size. So number 4, oops, we'll make it light blue. That's what I'm going to do it. Element size, number 4. As you go down a family, what's going to happen to element size? Increase or decrease? Increase, right. I don't think y'all can see this. This is too light. We need a different color. We'll do black. So it increases. And what happens as you go across? I told you it decreases, right?
Does that mean no gases are very small?
Yes. Yes, it does. They're happy with their electrons, they hold them tight. Nobody's stealing Princess, what's the little girl's name? Can't remember. What? Peach, there you go. No, Donkey Kong used to steal Princess Peach all the time. No, these are the British kids. I don't remember their names. Charlotte, is that the princess?
So for number 4, as it goes down, it increases?
As it goes down, it increases. As it goes across, it decreases. Okay, so those are our trends. That is periodicity. That's the concept. Okay, next idea, bonds. Okay, so first of all, there are 2 main kinds we're going to talk about. We're going to talk about more things too, but there's 2 kinds. The first one is ionic, and ionic bonds transfer electrons. So, this is what happens with table salt, sodium chloride. Sodium has 1 electron it needs to get rid of. Chlorine wants to steal an electron, right? So they work out a deal. This is an adoption. So sodium says, I got 1 I don't want. Chlorine says, I'll take them. So sodium gives its electron to chlorine. When it does, sodium now has a positive charge. It doesn't have the same number of protons and electrons anymore. Chlorine now has a negative charge. It's got 1 extra electron. Can you imagine that? What do opposites do? Attract. So that is what sticks them together. That's why table salt sticks together, is because the sodiums give their electron to the chlorines. Sodium becomes positive, chlorine becomes negative. Opposites attract, and they stick together like magnets. Can you imagine that? Y'all are doing good so far. All right, so ionics transfer electrons, covalents share electrons. So these are our nonmetals that work out, these are our divorce parents who are working out those custody agreements, okay? Compounds, the entire compound must be neutral. So go back to our table salt. Chlorine is positive 1. Sodium is negative 1. 1 minus 1 is 0. So we're going to do some math. It's not hard math. You probably could have done it in 3rd grade. But we're going to be doing some math where we make sure all of the compounds are neutral, that they're 0. Okay. All right, next idea. We're going to go into more detail about ionic. And I'm going to see if I can get this to roll. It does not like to roll because I drew pictures on it. Thought I was getting fancy with the pictures. It's rolling, yay! Okay, so Ionic is where they are transferred. They're held together because opposites attract. T-R-A-C-T. Opposites attract. Now they're made out of a metal and a non-metal. The metal is written first, like sodium. The non-metal is written second, like chloride. These ions, the metal ion and the non-metal ion, have special names. And how we're going to remember it is with some animals. So the first kind is the left, the metal one, is the cat ion. Now, cats are wonderful, sweet, positive, terrific little creatures, right? So we're going to remember that cat ions are positive. Now, some of y'all are looking at me like, no, I do not like cats. But wait, I can convince you. The other one is the anion. It's negative, it's the non-metal, and we can remember it from fire ants. His little body got left off. We'll give him some legs. There he is, he's a fire ant. We can all agree that fire ants are terrible, right? Much worse than cats. They bite you, and it hurts. In my old room, I used to have Miss Foster's room last year, there were fire ants building a mound inside the classroom by the door. They had come in from out, and there was a big old fire ant mound in our classroom. Kids were getting bit. So it's good that we moved over here, right?
Is it still there?
I sprayed it with some stuff, but they keep trying to come in. And if, like, at the beginning of the year when we cleaned out our drawers and we went out the door to clean them out, we were doing that last year and people were getting bit by fire ants. There are fire ants all outside that door. So much safer cleaning out the lab now. All right, so here are some examples. When lithium becomes an ion, is it going to want to gain or lose electrons? Lose. How many? 1. So what will its charge be?
Negative.
No.
Oh, wait, no, wait.
It's lost a negative, so now it's positive. Now, so the charge is +1. But we're all cool and we don't write the 1. We like to be like cool as math. And math has understood 1, so we like understood 1s too. Okay. What about magnesium? What would it be?
2.
2. So magnesium is +2. Now we write 2 because only 1s are understood. What about aluminum? What would it become? How many squares over is aluminum? 3. So aluminum becomes +3. And I left the L off. Aluminum is +3. Do you see how we're doing this? Okay. How about fluorine? What would it become? Does it want to gain or lose electrons? Gain. How many does it want to get? 1. So what's this charge going to be? -1. And we just put a negative because we're cool with the understood 1s. We're just as cool as math. Got that one? So what would sulfur be?
2.
It would be 2 or -2? -2. And what would nitrogen become? -3. So there's a pattern, and it goes like this. It's 1, 2, 3, skip, -3, -2, -1, zip, because noble gases don't make ions. Carbon doesn't really either. They can force it to be an ion now. They're using it for some cancer stuff, but mostly just it doesn't. It's the one that always does the sharing. It's the divorced parent. It's not trying to steal anybody's kid. It's not trying to get anybody's kid. It's happy with its own kids, and it just shares it with its former spouse. Can you imagine that? Y'all are doing good. Okay. Now, how do they get together to form compounds? Lewis structures help with this. Let me roll this up again. What time do we get out of here today with our advisement schedule?
I think 52.
52. So are we going to have time to do this?
3 minutes.
3 minutes. I want to do a little lab activity right now, and I don't think we have time to do that. So we'll just see how it says hands-on review break. 52. We're going to stop right there. We'll start with our hands-on review break, next time and continue with the notes. So like, share, subscribe.